Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right.
We are live in the aftermath of a massive hurricane.
Yes.
That's a bit of an exaggeration.
Yeah, there was a big hurricane.
It was briefly the apocalypse here for like a little bit.
Yeah.
Yeah.
North Carolina.
Yeah. There's a hurricane climbing up the United States right now, and we were on the edge of it. It was gripping, and now it is like beautiful and sunny, apparently.
Yeah.
So, because, storms last 25 minutes. Apparently.
But very intense.
Very intense. And then it's totally over. So our thoughts with anybody who is actually in the path of a hurricane, if you happen to be, I hope everybody is safe. But
Yeah. I hope so too.
Yeah.
Or at least I hope so too.
Well,
we all hope so.
We all hope so.
Yeah. I actually saw a giant truck just get completely obliterated.
Yeah, that was, yeah.
This
morning, Alex is like, hey, I'm going to be a little bit late today. Oh, this traffic is annoying. And then you find a truck that has been filleted open like a fish or something.
Yeah.
It's like, oh,
exploded.
good reason for traffic. This is a
Yeah.
very severe catastrophe.
Yeah.
So,
Pretty severe.
That was an aggressive scalping of an 18-wheeler.
Yes.
It's a bit crazy. Well, welcome everybody. We have most of the bookkeeping in the intro video now, which saves you time from having to remember everything. And that's very helpful. So I guess we'll just get right to it. Everybody, you can type your questions if you have any about electrochemistry anytime, and we will get to them. Of course, just as soon as we're able to. But there's one question that I think it was a couple weeks ago, and last week I meant to talk about this. Alex, you did talk about this last week a little, but I wanted to just share only to provide context, because I have some slides, and of course I was ill last week, and so you don't have my slides. You weren't. I just wanted to provide some context. So I'm just going to revisit this question about a shunt. So from this username with letters and numbers that I don't want to pronounce. They said, when you start measurement with a shunt, this is what this was about. You set the reference electrode potential according to what electrode you're using. So that means like what kind of reference electrode you're using, silver chloride or calomel or what have you. What would you set there now, since it changes from platinum to the reference when you're measuring and with respect to a shunt? So again, to address this a little more thoroughly, what I'm going to do is show slides from, I think it was the second, sorry, I'm getting the things ready here. No, that's not it. Not that. It was the second advanced EIS webinar, circuit fitting, that I had done some time ago. And there we go. I need to share my whole screen, because every time I try to do this, if I don't share the whole screen, the animations on like my slides don't work. So I need to share my screen. And so it's going to be a bit of an inception here. Give me a second. Okay. Is that working? Do you see?
Let me just minimize that. There we go.
Yep. Okay.
Well, yeah. So we see reference electrode.
Yeah, you see the animations happening, high frequency, blah, blah, blah.
Is there supposed to be a picture?
Not yet.
Not yet.
Now there's a picture. Do you
now
see
there's a picture. Yeah, I see electrolyte.
Okay, good. Okay, just making sure it's working.
It's a funny kind of electrolyte. It's just a blue square. I haven't seen an electrolyte like this before.
Did you know that water forms a perfect rectangle
itself?
Its surface tension is so incredible that it makes 90-degree angles at the corners.
I know.
That's what water does.
That's amazing.
I know. This is revolutionary science. Okay, so to the point here. Okay, so a shunt, right? The primary reason for using a shunt in an electrochemical experiment is to deal with the fact that at high frequency, you often have strange things in your impedance data. We call these artifacts or errors. There are names colloquially that we give them. For example, you'll see this in the literature. People will write the word artifact, something of that nature. But basically, at high frequency, we have a problem, and it is primarily a result of we call it sort of stray glass capacitance in the reference electrode. I'm not going to talk about it too heavily now. I can if there's an additional question. Alex touched on it last week. Suffice it to say, reference electrodes are a problem with high frequencies. So what you do is you add what's called a shunt. So in a typical 3-electrode experiment, you have your perfect rectangular electrolyte, and then you have working counter and reference electrodes, something like this. Now, don't worry about the shape and the size. I'm just drawing them for reference of this cartoon here, okay? We connect them to our potentiostat with these beautiful looking leads and alligator clips that I have drawn in PowerPoint, of course. So with the counter and the reference electrodes are connected to our potentiostat. We do our impedance. When we add a shunt, however, what we do is we add a parallel circuit to the reference side, okay? So the shunt consists of something like a platinum wire. It could be palladium, it could be something else, but generally it's something like platinum, very inert, noble metal, highly conductive material like platinum. And it is connected in series to a capacitor. It's usually in the range of picofarads, something like that. I've just drawn 100 picofarads here for reference. Those are connected in parallel, and that's connected to the reference line of your potentiostat. That is the shunt connection when you're employing one in this kind of configuration. Now, what does it do? Okay. And back to the question. So what, basically the question is, what's my potential? Because I'm using a shunt, I have a platinum wire. Well, to explain how it works and then why we should be concerned about this person's question, the typical impedance of a reference electrode for your reference, I guess, pun intended, is somewhere between usually 100 to 1K or 10K ohms. So it can vary in a variety of reasons, the frit, the concentration of electrolyte, and the impedance at the frit junction, and all sorts of things. But suffice it to say, it's somewhere between usually a kilo ohm, 10 kilo ohms is kind of pushing it in the higher range. Anyway, it's in that range, okay? The impedance of a platinum wire is basically zero. Let's just say it's effectively zero. It's probably really like milli or micro ohms. Wiring and everything has very low impedance. And so what we have instead here is a capacitor that offers an alternate path with an impedance that is inversely related to frequency. So when you're doing impedance measurements, the potentiostat will follow on the reference line the path of least resistance, right? All basically electricity, fluid flow, these things operate under the sort of phenomenon of following the path of least resistance or least impedance, if you will. Okay. Now to that point, if the impedance of the capacitor is lower than the impedance of the reference electrode, the potentiostat will measure the shunt. And I'll say the opposite situation right now. If the impedance of the reference electrode is less than the impedance of the capacitor and the shunt, the potentiostat will follow the reference electrode path instead. Now, again, a capacitor has the equation that the impedance is equal to 1 over j omega c, which means that the impedance of a capacitor is inversely related to the frequency, which means at high frequency, it's low, at low frequency, it's high. Okay. Now here's some numbers for you. At 1 megahertz, a 100 picofarad capacitor is about 1.6 kilo ohms. If you go down 1 decade of frequency, you go up 10x or of impedance. So at down to 100 kilohertz, the impedance of the capacitor goes to 10 times higher. Okay. So think about what this means practically. Again, path of least resistance. At a high frequency, the highest frequencies, the impedance of the shunt, depending on what capacitor I pick, is going to be lower than the impedance of my reference electrode. So at high frequency, 1 megahertz, let's say, the impedance of my capacitor is 1 kilo ohm. My reference electrode, let's just say it's 5 kilo ohms. Just make up a number. Well, 1 is less than 5. The potentiostat will sense the shunt. which means the platinum wire at these frequencies is technically my reference electrode. Keep that in mind. That's basically the question I'm going to answer, but I'm going to finish describing the path of how this works, and then I will finish addressing the question, right? The other scenario is where the frequency goes down, let's say at 100 kilohertz. Now the impedance of my capacitor is 16 kilo ohms. The impedance of my reference electrode, as I said, it's 5 kilo ohms. 5 is less than 16. Now the potentiostat will switch to measuring the reference electrode properly. And then you basically just have your regular electrochemical experiment, because as the frequency keeps dropping, the impedance of my capacitor just keeps going up. It's basically not, it's irrelevant. It's not a path that is going to be used. The impedance is so large, it might as well not be there. And that's what ends up happening. All right, that last question I will address after. So the question really that this person was asking was, at those high frequencies, when the potentiostat is using the capacitor with its lower impedance, the platinum wire is my reference electrode, but I put into my software, I want to do impedance at 200 millivolts versus silver chloride. Okay, well, when it's measuring the reference of the platinum wire, that's 200 millivolts versus platinum something. What is it? Who knows? Okay. Now I'm going to say this very directly. You probably don't care. Okay. The answer to what is the potential exactly, because you're using a platinum wire instead of a silver chloride, the answer is, I don't know, you don't know, and it probably doesn't matter. Okay. Now the reason it doesn't matter, you can see here. Here is, for example, a data set where a shunt was needed. Okay, so here's what looks like a regular Nyquist plot, right? Like you have a semicircle, you have a Warburg tail. Everything looks great until you recognize that this right here is a negative Z real. Well, that doesn't make any sense. This is one of these manifestations of this artifact where the data is poor. So in this case, the person, I think this was my data, so the person might be me, could have been a customer. I don't remember. It's been a while. Anyway, added a shunt with, I guess, 100 picofarads. You can see what happened was we still have a little bit of a tail in artifact, but overall, the data now is in the positive quadrant here. We have positive Z real. It sort of fixed the problem. You can look at the comparison Nyquist plot here. Black was with no shunt, red was with the shunt. So the shunt, eventually they all sort of line up and they look the same. But for the high and sometimes to mid-frequency region, we see a big correction with the red data. And the Bode plot shows that here. You can see a deviation and then they start to line up after a little while. And so you could determine, roughly speaking, what the impedance was and what the problem was. Okay. Now, one of the reasons, or sort of the primary reason why what I said is true, you don't exactly know what the potential is and you don't care, is because at the highest frequencies, which are the only frequencies that the shunt and the platinum wire is active in being used, there isn't really anything happening at those frequencies for which the exact potential matters. Because at the highest frequencies, the most that's really likely being measured is the uncompensated resistance, the IR drop, ohmic drop, all these are names for the same thing. So at the highest frequencies, you're just measuring IR drop. Now, life is never perfect, but for the most part, that process is independent of potential, because it's like a measure of the electrolyte strength and stuff like that. And so if the actual potential is off by a little because your reference is sort of this unknown platinum entity, it doesn't matter, because at those frequencies, you're just measuring this sort of fundamental property of the solution, of the cell, of the setup. And then by the time the frequency drops and you start probing processes that are potential dependent, like whatever Faradaic process, whatever redox process, charge transfer, capacitance, those kinds of things, once the frequency drops, well, by that point, hopefully, your shunt capacitor is no longer the preferred pathway, and it has switched, right? It has switched back. Sorry for the screen in the screen there. I had to stop sharing.
Yeah.
So at that point, you have switched back to the reference electrode and everything is back to normal, so to speak. And so you're probing the process of interest, so to speak. And so anyway, that is the general answer I can give you for that part of it, and why people often use shunts successfully for this kind of application. So, and Chris actually brings up a good point here. Current will follow all paths in the ratio corresponding to the ratio. That is correct. When I say the current follows the path of least resistance, Chris, it's not a lie. Okay. But when you consider that the impedance of one of them is, now in the case I showed, it was like more or less. So yes, I know things follow, stop pointing out reality is what my point. The point is, when one of them is like 7-8 orders of magnitude greater than the other, it might as well not exist. That's kind of the point, right? So for the most part. And then when it comes to the reference electrode, it is appropriate to consider that, because once the reference electrode lead of the potentiostat can sense a proper reference couple at, like, when the frequency drops, that's what it uses as its reference, basically. And then, as the frequency continues to drop, that ratio of impedances quickly becomes lopsided, right? And it is effectively the path of least resistance. Thank you very much. But yes, of course,
the majority current that follows the path of least resistance.
But even then, that's also a bit of, there's almost no current whatsoever. There's a lot of being taken for granted in this discussion, because the reference line has almost no current flow. It's not really none, but it's almost none.
Yeah.
So there's a lot here. The point is, what I said's true, and you can accept it. Anyway, all jokes aside, I hope that's helpful. That roughly, reality does add complications. Yes, I hope that roughly answers that question with some visuals anyway, just to kind of illustrate how a shunt, operates. And there's more I could have said. I'm trying to not talk for the entire next 2 hours. And, get to other people's questions. So.
Well, we do have a question that came in from Lev Lev asks and says, there are ways how to extract pseudocapacitance. Perhaps he's saying, are there ways to extract pseudocapacitance from CPE when it is parallel to a resistor? Is there a way to do it in the case of having a resistor and a Warburg in parallel to a CPE in a Randles circuit?
So whether or not you have a Warburg in your Randles element is
it shouldn't matter for extracting
it's irrelevant. Like, if you have R and a CPE, let me draw it or show you. Let me do a thing once I figure out how to share screen in this crazy software. Okay. I'm going to share my screen again so you can see when I pull up a circuit. So I'm just going to use this example again, just for convenience. So forget about all the shunt talk. I'm just trying to show you circuit fitting at this point. All right. So here's my Nyquist plot, right? Okay. Let's see if this works here. If I can kind of do a thing. So this right here would be something like this, is what you're asking here. So for example, I have a Randles element, R2 and Q1, and then I have Q2 would be my Warburg. I'm using a CPE here, but you can just imagine it's the same thing basically. Okay. Now it basically fits pretty nicely here. I don't have to do very much. I wanted to kind of adjust stuff here for you. But anyway, the point that I'm trying to make here is that I have fit Q2, which is the Warburg. You see the alpha is 0.5. I can lock it at 0.5 and make sure that's, what I want to make sure that it's a Warburg, whatever. The value for that CPE or Warburg element is here. And then I have the value for my Q, my pseudocapacitance. You see that It's estimated, it's pretty non-ideal, 0.76, whatever, 77 is my alpha value for that. Okay, you can see it kind of adjusting the fit here. But the point is that this value is independent. It's its own. You see how it moves that peak left and right? It's lighting up the blue peak, basically. This capacitance, measurement is independent of the Warburg one. And if I have a data set, for instance, like this, and I do a fit, this has no Warburg, this is like just a Randles element, well, then I do this fit and I get a similar kind of thing. Okay, well, now I have no Warburg, but I just have this capacitive element here and I get a pseudocapacitance. But do you see what I mean? Like, it doesn't, whether you have a Warburg element or not, you still have the ability to circuit fit and isolate the features of your impedance spectra. And by doing so, you can get a measurement for the constant phase element, or if you use a pure capacitor, you can lock, alpha at 1, whatever mechanism you want to do, basically. But it doesn't really matter whether you fit it or not. You still get the value. The nice part of doing circuit fitting with an algorithm like a software like this is that you get a value for each individual component, and that's one of the main benefits of impedance in general, is that you can get you can probe individual processes like charge transfer resistance and double layer capacitance and things like that by probing at different frequencies, and diffusion like Warburg. So whether they exist or not, I can probe them separately and get values by doing these kinds of circuit fits. So I hope that's clear, Lev. If you need a follow-up, or perhaps I didn't answer exactly the question you're asking in a way, please feel free to please feel free to comment and clarify.
All right. I have a question from FCB. FCB asks, why do we use 3 electrodes instead of 2 electrodes?
Because it's 50% more electrodes.
50% more electrodes. That's true. There you have a whole extra 1 electrode, and more electrodes, the better.
More electrodes, more fun.
More electrodes, more fun.
That's a dad joke for you.
Yeah. So the simple answer, sort of say, is that when you have you can do electrochemistry in the 2 electrode system. Oh, I should delete these. I don't need these anymore. Mm-hmm. In a 2 electrode system, you can do electrochemistry. It's not really an issue. But a 3 electrode system is usually employed whenever you're trying to measure the potential of just one electrode with respect to kind of a stable point. So there's a few ways of thinking about it. So one way I like to think about the potential between 2 electrodes is just to have is kind of this Fermi energy system. And people can see my screen, right?
Yeah, you're good.
So you may have these 2 electrodes and there's a voltage between them. And that voltage, and I can identify a level. This is like filled electrons of a metal. Is this? And then maybe I have one here. So I have these 2 metals. They're in solution. They're in some kind of solution.
Is your solution a perfect rectangle?
My solution is.
It's almost a
not
perfect rectangle.
Perfect rectangle.
But it does have sharp edges, just like water.
Sharp edges,
water. That's the main takeaway from today: is that water has sharp edges.
Water has sharp edges. So there's this, and actually, I'll make this a little clearer. This is a flat line, sort of say, but you have these two energy differences, and there's a reaction. These Fermi levels, and what the potential is governed by the Nernst equation, and there is a voltage difference between these. So you have a kind of a dotted line here, right? So there's a voltage difference between this level and this level, and so like let's say this is M1 and this is M2, just your 2 electrodes. And so you have a voltage difference, and you can measure that voltage difference between the 2 electrodes. So you're measuring a voltage in your 2 electrode system, and that's okay. But if your voltage is say, let's say this is 5. This is a 5-volt difference. And then you go to say 7. You change it so that, okay, maybe I have a 7-volt difference. Well, that can be achieved several ways. This can go down, this can go up, but you don't know by how much or which one is which. When you have a voltmeter between these two electrodes, you can measure the voltage difference between them, but you don't know, relatively speaking, which one has gone up, which one has gone down. Maybe did this one go down by 1 volt? And then this one went up by 1 volt to get 7 on either side. Maybe one of them just went down all the way by 2 volts, or where the other one went up by half a volt and the other one went down by 1.5 volts. So you don't know. The big thing is you have no idea how this, the voltage difference is 7 volts, but you don't know by which. And even when it was at 5 volts, you don't know by which or by how much one is changed or the other one has changed. So what is done is we typically add a third electrode. This is why we add the third electrode. So we have a third electrode in our system, which is a reference electrode. And the reference electrode, let's just say, has a Fermi level that doesn't move. It's stable. So this one, we'll just call this M3, which is our reference electrode. It's stable. It's designed in such a way to be stable. Reference. It's designed to be stable. It's designed in such a way that this does not move. It's what we refer to as an ideal non-polarizable electrode. If you were to look at the graph of the voltage versus the current, you'd get something like a straight line. It doesn't matter, and then of course it deviates at certain points, but over a wide range of currents, the voltage remains the same. So what that means is that when you have a voltage, or when you have a voltage difference like M1 or M2 is changing, you can measure the potential of M1 and M2 with respect to this reference electrode. And you'll know that, M1 indeed went up by 1 volt, or M2 indeed went down by minus 1 volt, because this guy isn't changing, but this guy does change. And this guy does change. So that is the purpose of the reference electrode. It creates a stable reference point. That's why we have these 3 electrode systems. But there are plenty of systems out there that don't use a third electrode. Just makes it tricky to kind of know in a more absolute sense what the energy or what the potential is of your 2 different electrodes. So hopefully that clarifies a little bit about why you either would or wouldn't use, or what's the purpose of having a third electrode, why you use 2 rather than 3, or 3 rather than 2. And that's the general gist of it. So FCB, let me know if that was clear, or if you need further elaboration on 2 versus 3 electrodes. Let's see. And I'm just checking.
Mm-hmm.
Yeah. So there's so nobody's on. I mean, there are people on LinkedIn watching, but there's no questions on LinkedIn that I have seen.
Well, we have a second before the next questions hopefully come in here. I'm going to plug my own event next week. So I will be reaching out, I think, via email. We'll probably make some social posts as well. It's been a while, and so I am hosting webinar next week. So you can see on the right side of the screen here, it's on our website, but next Wednesday on October 2nd, I will be giving a webinar on electrochemical impedance spectroscopy, EIS, theory and fundamentals. So I will have the registration open by the end of today. And as I said, I'll be sending out an email as well to people. If you're on my list, perhaps you will get one inviting you and showing you where you can register. So I hope that you all join me. I'm going to be giving some webinars over the next 1 to 2 months or so on topics of impedance. And I hope that you'll join me. So there you go.
Very good. FCB has a follow-up question. How do we characterize metal peak and ligand peak by cyclic voltammetry? So I think FCB, what you're referring to is when you're doing cyclic voltammetry and you get a peak, how do you know that that peak is associated with an electron transfer to the ligand of a metal complex, or if it's directly going into the metal itself, say changing the oxidation state of your copper or your cobalt complex or something like that? In general, I don't think there's anything in the cyclic voltammogram per se that is unique to a metal versus a ligand, sort of say. Generally, we make the we kind of, I don't want to call it an educated guess, but generally speaking, we know what the oxidation reduction potentials are to a certain degree of certain metal ions. Like we have these electrode tables that are full of just like, what's the copper 2 to copper 1 or copper 2 to copper 3 redox potential. And so we have a rough idea about what that potential is. And then you can use ligands in your complex, within your complex, to actually move, to use electron negativity to either change what that oxidation state is. And so you end up seeing small shifts in that potential. So let me just kind of to illustrate that, just to make sure we're kind of on the same page. But you have your electrode, and then you have a molecule. So this is again like you have a metal, and maybe it's charged, and it's got a bunch of ligands. So it's got usually most of these things got like four ligands. Let's go out here. I guess maybe I can try doing this. It's been a long time since I've
the like 3D thing where it's
the
going
3D
in or out
thing.
or whatever.
Yeah,
I was used to like those actually.
Yeah, let's see if I can. I don't know if I can do them or not. All right, so let's see. I'm gonna say that this is going out towards you, and then this is going behind you. Just nice, but you'll have these 6 ligands. Generally speaking, that's just general. And so the question in turn is, when you have an electron transfer, let's say it's a reduction, how do you know that it's from the ligand, or it's to the ligand, or directly to the metal? And so my thought is that most of the information about these metals can be found in tables, that like, M plus E is in equilibrium with M, and there is some E naught associated with it. If you do, something, well, let's just say 5, you'll be able to observe that, at this potential on my electrode, I'm getting an electron transfer, and maybe I only get slight deviations based on the choice of ligands that I have around my metal complex. The other thing typically is, if your complex has very big ligands, it's usually very difficult to have any electron transfer directly to the metal if the ligand is so big. There's too much distance between the electron to the metal. That's the other thing. You can also look at things. One thing to also keep in mind is heterogeneous versus homogeneous electron transfer. So heterogeneous electron transfer is, say, when there's actually kind of a bond, sort of say. I'm just going to do this for now. There's actually more of a bond between the ion in question and the electrode surface for the electron transfer to occur. So you have your electron moving here, but it's kind of bonded, as opposed to here. This is what referred to as homogeneous electron transfer, where the electron's actually tunneling through, say, a solvent molecule to get to the ligands and stuff. And so the choice of the metal that's being used will also determine whether or not it's a homogeneous or a heterogeneous electron transfer, generally speaking. And usually when you have these types of things where it's a homogeneous transfer, the chances of it being directly to the metal and not through the ligand, I believe, and I don't know for sure, but I believe that that's another kind of indicator that if you do have homogeneous electron transfer, it is directly to the metal. But these things can be assisted. So I might do things like change the ligand. It's not just from the electrochemistry. You have to do other techniques, other kinds of experiments to determine the nature of the electron transfer. If there's charge transfer within, could you put the ligands on another metal? That's another thing. Like if you put the ligands on another metal and the potential with which they're getting reduced is the same, there's a pretty good chance. And if those two metals are far apart on the table, that's a pretty good chance that you actually have a charge transfer to the ligand as opposed to the metal. So those are kind of the ways. It's not just from cyclic voltammetry, generally speaking. You actually may be able to do big cyclic voltammograms where like you have a wide potential window and you get multiple electron transfers. Then you have, that gives you more tools to kind of elucidate the nature of the electron transfer to the ligand or the electron transfer to the metal.
Is there any way that just occurred to me, but is there any way that like the Savant kind of shapes of different I don't know if these are all P-set or just in general, but like there's all the shapes of voltammograms for different situations. Is there any way that, because my impression is the same as yours, which is to say that CV by itself is probably not enough to elucidate which of those is happening. But is there some way you think that, like, I don't know, more about the like
the shapes?
Yeah, the shapes that you showed that reference like a couple weeks ago.
Yeah,
like the Savant different ones. Like, if it looks like this, it's sort of like pseudo reversible, blah blah blah, or whatever it is. Is there any way that any of those shapes would allow you to make any conclusions from the CV shape itself to say, oh, this might be homogeneous versus heterogeneous, or this might be this or that? Maybe we don't know the answer. I just made me think of it.
Yeah, the Savant table, usually the X and Y axis is like, unless you've been studying it, it's slightly bizarre, but it's like it all has to do with catalysis at the end of the day. Yeah. So like, how much of the catalyst do you add? What's the concentration of the substrate that you add? Do you have more substrate versus catalyst? What ratio of those? And then how do you change the scan rate? So changing the scan rate's the other thing you can do to start to elucidate the mechanism, sort of say, and maybe even get some kinetics information. But I don't know if it tells you enough about whether or not your peak, the electron transfer, is specifically associated with the metal or the ligand per se. Yeah. But that's a good question though. I wonder about that.
It seems like the only way you'd be able to do that is with your own kind of like proof of concept. If you have some, let's just say some metal ligand complex with like the largest ligands you've ever seen. You know what I mean? Like they're like 5 trillion
Dalton.
Whatever, right? And then it's like, well, this is guaranteed to be ligand transfer, right? Like
something like
heterogeneous. There's no way this is going right to the metal core.
Yeah.
And it looks like this. This is what the peak looks like. Okay. These scan rates and these, experimental conditions. And then you have one where you're pretty sure it's homogeneous right to the metal core, etc. And it looks like this. You might be able to like, but that probably is difficult from the perspective of having to synthesize or populate your experiment with these two different, metal ligand complexes. And it's like, how, I've never made metal ligand complexes, and I don't know how difficult they are to synthesize or test, or how stable they are. Like, there's a lot of open questions here. Anyway, absolutely. I think probably you could, like, in theory, work out the extremes of those two sides. That, like, the largest 5 trillion Dalton complex, and then like the tiniest one that just has like a little tiny ligand, and you can see what it looks like for the electron transfer in either of those cases, and see if there's any determining, physical characteristics on the graph, let's just say, that that suggest one or the other.
Now you definitely have to do some kind of science experiment. And I think Chris even made a good comment. He said that I suspect you can get time domain data that will give you more information about the ligand activity. Yes, I think there's a lot of people like, we collaborate with Julian Dempsey, who does electrochemistry and on these inorganic complexes. She uses a lot of spectroscopy as well to study these ligands and their complexes and things like that. So, I'd say FCB, that's probably, like, you have to do a couple experiments. You have to change your synthesis conditions. You have to experiment with the ligand. You have to experiment with the metal, changing those things to determine if the peaks line up to where they should be, to determine if it's ligand or metal transfer associated with a peak.
Looks like we got a couple other questions here. So first is that why in bulk electrolysis we stir the solution, in CV we don't stir it, and if we leave it stirring, what happens in CV? Try it and find out. Seriously, if you're wondering what happens when you stir and do CV, try it. The short answer, I suppose, is that you don't always stir while doing bulk electrolysis, and you don't never stir or mix the solution, I guess you'd say, while doing this is not an accurate binary for these two things. Like, I mean, folks do still bulk electrolysis, and stirring bulk electrolysis, and then vice versa. So, one of the reasons why, I suppose, if you're going to say there might be a likelihood that someone would stir while doing bulk electrolysis, might be because when you're doing bulk electrolysis, typically you're referring to chronoamperometry, which is where you're setting the potential, measuring the current over time. And you're often doing that to generate product, like like at some potential, I am doing some redox process that generates some product, right? And I'm trying to generate as much product as possible over some period of time, or generate as much current so I can measure it, put it through GCMS, measure, whatever the case may be. Okay. And as Chris notes here, CV, basically the point you're making here is the diffusion limitation. So when you have a still solution, you very quickly run into diffusion limitations, which is to say the diffusion layer at the surface of the electrode, the thickness of that diffusion layer starts to grow, which is why the Cottrell equation describes over certain time ranges that the current decays with the square root of time, basically. And it's because the diffusion layer grows thick. Essentially, you're waiting for the stuff to get to the surface of the electrode to continue reacting after a while. And by stirring or mixing the solution or spinning the electrode or something, you force convect more and more reactant to the surface more quickly. You can generate more product, and then you might be measuring it or generating your product more quickly. So sometimes it's just to generate more stuff, right? But that being said, I mean, there's an entire field of rotating disc electrode electrochemistry where not stirring the solution, but you stir the electrode during cyclic voltammetry, and you will discover differences in the shape of your CV, for instance, or your LSV. Often that takes the shape of, instead of a peak, you get a plateau, because you still have a diffusion layer, but it is set based on how much you're stirring, essentially. And so you very often, when you mix the solution doing CV, you will get a kinetic increase or decrease, whatever the direction is, in the reaction of interest. Once you hit that potential, the current will exponentially increase according to the Butler-Volmer equation when you reach those potentials, and then it will not usually make a peak, although in some cases it does. It depends on a variety of factors, but basically you will have a slightly different situation occurring in your cyclic voltammogram by stirring. And as I said, some people certainly do that, just that experiment. So do it and see what you see. But again, very often when you're stirring a solution, the electrodes are at the top and the stirring is at the bottom. And so sometimes what happens is the solution is drawn away from the electrodes, which can not exactly behave ideally in some cases, because if you want the solution to be, if you want your reaction to be going more faster, right, more convected, you want to push the solution towards the surface of the electrode, not away from it. So in a lot of cases, that's why people rotate the electrode rather than put a stir bar in, you know what I mean? But the effect of mixing the solution, I think in a lot of cases can still be effective in, mixing, reducing diffusional effects and things like that.
Yeah, I think a lot of people, just even to your earlier point, like in bulk electrolysis, they're trying to get solution towards the electrode to just generate species. In CV, it's more of an analytical technique. So stirring the solution actually messes around with this relationship. So I'm just going to share this very quickly. This is the Nernst-Planck relationship. So the Nernst-Planck relationship describes the flux of your analyte towards the electrode surface at a distance of x, and it's described by all this stuff, which is just, it's a very complex differential equation. But each section can be broken down. There's a diffusion element, there's a migration element, and then there's a convection element. And when you use equations like, say, the Randles-Sevcich equation, or if you want to describe, the Cottrell equation, or different types of equations that help us calculate things like the diffusion coefficient, which is usually what people are after when doing CV, or they want to get kinetic information, they can omit all this other stuff when they say add a lot of electrolyte. But in this case, this last part here is the convection. If they don't stir, this component goes away, and they only have to solve a much simpler differential equation. And so by solving this more simple differential equation, we can get more useful information. That's another just reason why people do CV without stirring, because this will mess up their results that way.
Analytically, it's harder for sure.
Yeah. And then I guess there's just a quick question because there's another one. But for cyclic voltammetry, we always choose 100 millivolts per second as the scan rate. I guess the question is, why do you choose 100 millivolts per second?
Or should you choose?
100 millivolts per second? I think it's just kind of like a starting point. There's a lot of experiments that go much, much slower than 100 millivolts per second. There's a whole series of fast scan cyclic voltammograms. There's also linear polarization resistance, where you have very, very slow, like 0.1 millivolts per second. So 100 millivolts per second is just kind of the general middle of the road scan rate in cyclic voltammetry. But if you find that you're getting better results at like 50 or 200, like, you should go with those instead. That is usually fine. All right. So, and of course, let us know if you want further elaboration on these questions about cyclic voltammetry versus bulk electrolysis and stuff like that. So there is some follow-up from Lev. Again, just calling them Lev. There is an equation related again to capacity of CPE that looks suspicious to me. For a Randles circuit, R1 and then R2. So R1 is like the solution resistance. You have R2 charge transfer resistance. and then Q as the capacitance, the constant phase element in parallel. So for that Randles circuit, capacity is a function of both resistors, R1 ohmic and R2 double layer. So it is logical to assume that R1 does, assume that R1 does not have to play any role. The formula is C effective, the effective capacitance, is equal to y sub 0 raised to the 1 over n multiplied by 1 over R1 plus 1 over R2 raised to the n minus 1 over n. If R1 is less than R2, it has more influence than R2. 3 exclamation points and a question mark. So
I can show you where this comes from.
Yes, I would like to know where this comes from.
Yeah.
C effective.
So it depends on whether you have a Faradaic or a non-Faradaic system. In short, in long, here's a paper. I'm trying to just find the right place in it. But okay, so effectively what you're talking about is converting CPE to capacitance. And why does it involve R1 effectively? It seems kind of counterintuitive. So the short answer is that it's not really, there are different methods to which people have suggested to convert constant phase element fits, I guess, to effective capacitances, right? And this paper, for instance, discusses those. So I don't have the original. This is like one of the newer ones that discusses it. There's a few earlier ones. There's methods by Schuh and Mansfeld, and then Brugge as well. And then Hirschhorn, I think, has one. There's a few. So you can see here, I'll just sort of walk through this section here. I'm not going to walk through the whole paper, obviously, but among all models, those presented by Brugge et al., which is equations 4 and 5. One of these might be the one that you wrote. I don't have your question in front of me. I think this is the one that you wrote. It's like there's RS is R1 right here, and then RP. And so what you're talking about is when RS is bigger, it's because it's inverse, or when it's smaller, excuse me, when it's the inverse of it, it has more of an effect, not necessarily because you have this n-1 factor here. So it's not necessarily exactly the case, I think. But anyway, what was I talking about here? Right. So Schuh and Mansfeld gave equation 6, and so there's another one right here, for instance. What you tend to find, effective capacitance for a blocking system, well, equation 5 and 6 are effective capacitances for a Faradaic system. What you're talking about, for instance, where, okay, well, what am I going to do? Because I have a situation, if RS is really small, it's going to like really impact the measurement of my capacitance. And that seems counterintuitive. Why would that matter? I think the short answer is that what I can tell you experientially is that when I have done this exercise, for instance, and I've gotten some CPE values, which gives you this Y0 right here. This is like the capacitor. We call it Q, or you call it, I don't know, there's different, there's different terms for it, if you will. This is the definition of the CPE up here. Where the heck is it? Sorry. Yeah. So this is how they define the CPE. So the impedance is 1 over, sometimes you put Q for this Y0, sometimes C. Anyway, they use Y sub 0. So just so you're aware what the variables they're using, right? And then some people use alpha, they use N for whatever reason, just so we're clear on the terminology. And so basically what you're doing is you're using this alpha to correlate. And so you can see if N is 1, this is 0, this goes away, C is equal to Y, 1 over 1. So all of these basically boil down to if N is equal to 1 or alpha is equal to 1, the capacitance is just equal to Y. And so the first answer, I guess, is that, oh, well, this is strange because RS is involved, and the other ones, it's involved only in this expression, which is the one by Shu and Mansfeld, I think, and then or Brugge. I apologize for messing up which references these are from. All of these different ones are from different researchers from different years. The paper you're looking at now is one that compiled these methods. So that's why I prefer this paper. It kind of aggregates everything together. There's more discussion in this paper too. And I might be misrepresenting, and I apologize if I'm doing so. They discuss which ones might be better for which cases. They also, in this paper, suggest, I think, a much more complicated overall solution. Like there's some more mathematics in here. It gets a little more complicated. I'm not saying that to disparage it. It's probably quite a bit well reasoned. It's just that the simplest Shu and Brugge methods are sort of more known for some time. And anyway, that's where that equation that you're using, I think, comes from. I just like this paper because it kind of aggregates everything pretty nicely. In any case, again, just to the point is that when you have CPE data and you use all three of these, very often they're similar, right? Again, I think you ought to figure out which one applies most to yours. For instance, this one says, if there's a blocking system, so that's sort of a non-Faradaic situation, you would use this one here because you don't have an RP, you don't have any charge transfer processes. When you have a Faradaic system, you would use equation 5 or 6, which is the one by Shu and Mansfeld. And you can see, it's like if you're concerned about this equation, you don't have to use it. You can use this one instead. There may be situations where if you have a very odd combination of values for the RS and RP, R1, R2, whatever, that it gets wildly inaccurate. Like this is not unusual because these are, I believe, largely empirical relationships as well, which means that they don't necessarily apply under all conditions, and they're somewhat of an estimation. And so I would encourage you to sort of use both of them. A lot of times, again, the values you get for the effective capacitance might be similar, and so pick which one seems most applicable to your research, your system, I suppose. Or use all of them and try to compare and contrast. I will provide the DOI for this paper for you because if you'd like to look it up, I would encourage that as well. There's one other reference too that I might try to look up while we move on. I suppose there's another. It's like a paper. I know it's a bit strange, but there's a paper that sort of has. It's like the supplemental section has a really good aggregation of these things. I've done some looking into this in the past, as I said, and it's a little hard to wrap your mind around, but in any case, there are a lot of different equations you can try to use. So here, this is a effective capacitance from CPE paper DOI. So go ahead and look that up if you wish. Are there some other questions here?
There are other questions that have come in.
So yeah, I'm going to try to find the other source just for context. If you need me, I'm going to be briefly scouring my email for a thing, and then I will rejoin shortly.
So FCB has a question for CO2 reduction. If we get CO and then we added ammonia, if there's a possibility to get urea. I think in theory, it's possible. Now, I personally do not have any knowledge on, I know a few things about CO2 reduction. I don't know very much about converting ammonia to urea. I haven't studied that. But generally speaking, just what I found is CO2 plus ammonia is currently in a 1-to-2 ratio. So 1 part CO2, 2 parts ammonia does get you urea, just in a synthesis pressure temperature situation or chemical engineering system. So that does not involve any electrochemical reduction or oxidation. I'm sure some of those things are happening a little bit. Different things are getting oxidized and reduced when you go from CO2 to ammonia. But if you started with CO, would you get to ammonia or would you get to urea kind of faster? It might be possible. I think when you have these types of systems, there are a lot of things that could be happening. Like, so you have your catalyst, you have CO2, you have CO, you probably have water as well, because even if you didn't add water to your system, water is a byproduct of urea production with CO2 and ammonia. It forms, you lose an oxygen, and the ammonia loses, two ammonias lose a hydrogen each, and they form water. So if you just started with CO, you would need to put the nitrogens somewhere, because urea is it's just let's see, CONH2, like there's two of it. It's also called carbamide. It's a diamine. So that's something I don't. So the thing is, I don't know. I think there's a possibility, but CO also, just from a chemistry perspective, from a catalysis perspective, CO is known as like a poison for most catalysts. Sometimes CO is what we're trying to avoid, or we want to funnel CO very quickly into another catalytic system. You can actually form hydrogen gas, which is sometimes much more useful of a material. You can use the water gas shift reaction, or you can use hydrogen gas and CO to do a syngas reaction for catalysis purposes. So, but that is something to keep in mind. So the answer is I don't know, but those are all things that I would think about if that's a project that you're working on. I hope that was helpful, FCB. If you need more information, or if you want more clarification, or if there's a certain aspect of that, ask us. But I don't think Neil and I, we haven't done urea production. Actually, I feel like a lot of people are just trying to oxidize urea. But yeah, converting ammonia and CO to urea, possible. Maybe you form hydrogen gas instead of water instead, but that's all. That's all, I guess, theoretical. Stoichiometrically, it works, but the actual doing it is hard. Okay, so we have a question from Andrea. Andrea is asking, there is a default method for performing Mott-Schottky measurements with standard equipment. Do you think it's better to measure impedance at each potential and extract the equivalent circuits for a more accurate calculation? Or should the default method provided by the equipment be considered precise enough?
What's the equipment and what's the default method? Because probably the answer to your question is yes, you should do, how did you word it? You should measure impedance just at manually, each potential and extract the equivalent circuits. So one of the things that I've observed is that commercially, with most potentiostats and Mott-Schottky experiments built into the software, what you're calling the default method is not great. It's not accurate, because most of the time what is done is one high frequency point per potential. So step at some potential, measure a high frequency, change the potential, measure a high frequency again, change the potential, because dimensionally you can extract a value for capacitance from 1 point of impedance. You can do it. Now, is that accurate? No, it's not. Sorry, I'm not going to, I'll answer my own question. No, it's not accurate. Maybe in some specific instances, in certain cases, if you're lucky and you pick the right frequency, you might be okay. But most of the time, this is a very inaccurate way to actually conduct Mott-Schottky. I don't know where this came from. I just know that it's what's most often done. Somehow, somewhere, years ago, I suppose, some people, not at my company, not mine, don't blame me, folks decided it would be a very easy, shortcut to program Mott-Schottky this way. I do not recommend this method. That's why, for instance, you asked the question, so I'll give you the shameless plug here. But in our software, in our Mott-Schottky program, for instance, if you need to make the question go away.
You
got it.
Okay.
Yeah, no worries. What you can see is that the default Mott-Schottky mode for our software involves the potential steps. So, whatever, you're going from whatever potential to whatever potential, stepping however often, right? And the default for us is multi-frequency. Okay, so you typically don't need a huge range necessarily. Now, what you described is doing like full impedance spectra at every potential. Absolutely, you could do that, especially if or I could say it both ways. Whether or not the situation at your electrode, how many Faraday processes, how many charge transfer processes, how many Nyquist plot semicircles are you going to get? How many plateaus in the Bode plot are you going to get? Like if you know that, you can isolate which capacitance is the space charge capacitance effectively to make your Mott-Schottky plot from. And if you don't know, well, better to do a wide range of frequencies to elucidate that. In the case of a multi-frequency Mott-Schottky, like our software allows for you to do, you can try to do a range of frequencies around where there's mostly purely capacitive behavior going on. Because quite often it is possible to do Mott-Schottky from analysis of full impedance spectra, and you have a bunch of circuit elements. But a lot of times you're hopefully having mostly just capacitive behavior, because that helps you isolate the space charge capacitance a little more easily. If you have like 4 or 5 different capacitive elements, it just makes it difficult. Which one is the space charge, and how do I fit this properly? It's a lot, like there's people that have written papers on this kind of thing. For sure, to be clear, it can be perfectly valid to do this super complex kind of analysis. But if you're trying to simplify things, getting a single point, which is this one, like 1 point, repeat it once or twice or 5 times. That's usually the default method. Well, I picked 1 kilohertz. Okay, 1 megahertz. Well, what frequency should I pick? Is that even capacitive? Is that an appropriate place to do it? Right. Some of those questions the answers are almost certainly no, and maybe you get lucky, but it's not the best place to do it. So, I think most probably you will do yourself a favor by doing something in between the default method of just 1 point, like 1 frequency, right? And a full-fledged impedance analysis, if that's a little too much, right? At the very least, you can do something like a range, do a fit, kind of, a lot of times what you're actually getting is like the slope on the Bode plot to extract the capacitance value. That's a bit more complex than maybe you might understand, but effectively your thought process is wise, is what I would say, right? Which is to say that to do a more robust electrochemical analysis, impedance analysis at each potential is going to almost invariably get you more accurate measurements of the capacitance, which will then get you more accurate measurements of the flat band potential in the electron donor density from your Mott-Schottky analysis. So I do recommend that.
Nice. We have a question from Hab G. What would be electrochemical experiment you would do if you have a material that you believe would be promising for CO2 reduction? Cyclic voltammetry. So yes, I think cyclic voltammetry is definitely a good technique to evaluate whether or not you have a good material for CO2 reduction. Generally speaking, what I've kind of observed or seen, or at least what people do, is they'll have their electrochemical cell. You may even want a separated cell, but they'll have their solution. You will bubble CO2 into your solution. So that's CO2 in. You're going to have maybe a counter electrode, might be a platinum wire. You may want to isolate it to make sure that it's not interfering with your CO2 reduction. You have your working electrode. This is your promising material. And then you would have a reference electrode. So you could do this in a standard 3 electrode setup, sort of say. So you have working, which is the material. You have reference, and then you have counter. And you'd want to do kind of 2 experiments. You want one where CO2 is being bubbled in. You'd want to have one where nitrogen's bubbled in. And you would probably want to do this in a buffer solution so that the pH doesn't change. So this solution needs to be buffered. And as a first pass, right, you're just trying to evaluate whether or not your material has any hope of doing CO2 reduction. What you're going to look for, or what you're going to hope for, is that you're going to get a CV that maybe looks like this. Or actually, let's do this the right way. So you're going to do something like this. So you're going to start your experiment at a positive potential. You're going to apply a negative potential. You're going to reduce something. Maybe this goes here. And then you're going to have something like this. Something. So this is your CV. So this is the reduction of your just catalytic material, right? And this is just in nitrogen. And then when you add CO2, I'll do this in red. You're going to hopefully observe something, maybe along the lines of this. So you get this huge like current, and I'm going off the screen, and you're probably going to have an irreversible reaction. So this is with CO2. And you ideally want to do this. It should not matter what scan rate you do, but this is the first approximation of like, when I made this material, I have this material. Does it have any hope for CO2 reduction? You may observe that like, you have to go all the way out here to reduce CO2. It needs to still be at the potential. You'll still have your peak associated with your normal, your system, and it would be about the same height. But then when you get this type of behavior, that usually indicates CO2, and then double check the potential with which this occurs, because you could also be generating, hydrogen as well as you're applying negative voltages and getting negative currents for the reduction reaction. So CV is probably one of the best early steps at, this is a relatively simple setup to just know whether or not your system can do any CO2 reduction. And then you would do a bunch of other tests to, do C13 labeled CO2. You might want to do an electrolysis experiment afterwards to see what products do you get. So HAB-G, those are kind of the CV is probably the easiest, most straightforward and simplest experiments that you can do just to get started to evaluate whether or not your material can reduce CO2. That's just a start. So hopefully that is helpful. We have a question. It's not an electrochemistry question.
I don't know if I understand.
Yeah. This person just says, I have a test tomorrow, and then they read in the 2nd grade, and I don't know what to read. So I think it's they're looking for a book recommendation.
Or are you saying you read at a 2nd grade level? Or you read in 2nd grade? Is it read or read? Because that could be past tense. Because I also read books when I was in 2nd grade.
No, that's true.
I'm not sure
too. Yeah,
I'm not sure what this is asking.
Yeah,
so it's a little perplexing. I'll be honest. I don't know what to read. I don't know what to read either. But right now, what I'm reading is your question, and it's confusing me. So
yeah.
Good luck on your test. I guess.
Yeah, I might look, do a Google search for best second grade books and find one that sounds interesting and hopefully be able to read it. And that way, but if you're having a test tomorrow, I bet that your book is probably on what the teacher probably assigned the book. They didn't give you the freedom to choose. Like,
that's usually what happens in school.
Yeah.
That's why I didn't like to read when I was in high school as much.
Oh yeah.
I didn't really like to read very much when I was younger.
Yeah, me too.
So something about being told what to. There were some books in high school or maybe in college, I guess, that I didn't hate, having to read. But it's not surprising I became a scientist because
The Art of
Electronics by Horowitz and Hill.
Yeah, we had.
It's just some light reading, just a little bit of light reading.
Oh God.
So I feel like it's some of those reverse psychology things. Now that I'm like an adult and I can pick things to read, I read more often probably as an adult than I did as a kid, because no one's telling me what to read, and it's like, well, then I guess I will.
I actually the issue for me, I didn't like reading when I was a kid. First of all, just because I was a kid, I just didn't like reading, and I preferred math science. But I found out later, I'm like, oh, they're these, like, I just like nonfiction. They rarely have books on nonfiction when you're growing up. They're all like fictional stories or something like that. Like, I prefer nonfiction. And once I discovered these, I was like, oh, I'm going to read these. I like reading nonfiction. I always like learning something. I don't need to know about, John Steinbeck and, the Grapes of Wrath, or I don't know. It's like,
some of those,
the jungle.
Some of those are good. Some of them are annoying to read or whatever. And I never liked poetry very much.
Oh yeah.
Because I'm way too simplistic, and it probably is more of an evidence of why I went into science. But I always felt like if it doesn't rhyme, it's not a poem.
Oh yeah.
like at least if it rhymes, you put some effort to make the end of each line, rhyme, and then it like flows and it's kind of fun to read. But if it doesn't even rhyme,
I don't. Yeah.
Are you even trying?
Yeah. Just like
there's
Ethernet cords. Adapters are gray. The gray of my computer.
The grayness wells up deep inside me.
Deep inside. Luckily, we have ducks.
Ducks quack.
Done. Yeah.
Quack like what I call my knowledge of science. I'm a quack.
I'm a quack.
I'm an imposter. Scared deep inside. The end.
The end. Yeah.
Like, give me $1 million. That's a poem.
Yeah. Yeah.
I never liked poetry.
The Def Jam.
Can we ask us anything of electrochemistry plus Def Jam electrochemistry poetry? How many of you by raise of hands? I know I can't see you, so just go with it. Would enjoy electrochemistry Def Jam poetry. This is an untapped market, I feel like.
Yeah. Electrochemistry Def Jam.
Well, until then, I guess we can answer Santiago's question.
Yeah, so that's a good question.
So for a CV measurement of a supercapacitor at a scan rate 10 millivolts a second, there is a maximum current. When the scan rate increases, this current increases. What is the physical meaning of it? Does it mean there is a more conductive material? However, the capacitance decreases when the scan rate increases. Well, I think you have your handy dandy.
Oh,
well, see, what's curious is you're saying, are you getting a peak?
The capacitance decreases when the scan rate decreases.
The capacitance shouldn't technically change, but I guess what isn't clear is you're saying there's a maximum current. So are you getting a peak? Because it just sounds like if you're doing CV on a supercapacitor and you're seeing a peak and you're getting some sort of Faradaic response, that's not probably where you want to be scanning. Like, are you like, or you're just saying a maximum current, like it's plateauing somewhere, which what I would expect to see. Alex has drawn this.
Yeah. I mean,
a number of times.
I was just gonna
draw the
kind of thing. Yeah, you draw it.
Make me draw it. Fine, I'll draw it. Good. But like if you're doing your CV, right, and you have voltage and current, and you have, let's just say 10 millivolts per second. On a capacitor, you're ideally getting something that looks like this. And so when you have maximum current, I assume you're just referring to like where this level is, like that this is,
Yeah.
you know, this is hopefully around 0. Let's say this is, you know, 0 right here. And so basically up and down, you have some current, you know, this is like plus I, and this is minus I. It should hopefully look like this. This is typically how you're measuring it.
Mm-hmm.
And then your capacitance is measured. The current is equal to the capacitance times the scan rate. Try to draw it so it's not V. You know, it's supposed to be like it's nu or upsilon or something like that. I think my colleague Tim always yells at me because he says it's actually upsilon.
Oh, it is actually epsilon?
I think so.
I've been doing nu.
I know I always do nu, but he was all on his
high
horse about it, and I think he's right, but I don't want to admit that he's right, so don't tell anybody. It's actually upsilon, so it's rounded at the bottom here technically. Anyway, I digress here, but the point is that to get the capacitance, right, the capacitance is just equal to. Did I do that right? Did I do it backwards? I always screw this up for some reason.
Oh, what
is this right? Capacitance times the scan rate. Yeah. So the capacitance is the current divided by the scan rate.
Yeah.
Divided by, I'm gonna draw upsilon, draw it properly. So technically what you should see, for instance, if you did 50 millivolts per second, you should get a larger plateau. I'm running out of space. It should probably be higher than this, but anyway, you would get something like this. It should still be centered around 0. And then your plus and minus I, and it's half of the CV, by the way. That's the other point to make. You would like it's half of this envelope or whatever you'd say.
Mm-hmm.
And so this I for the 50 millivolt case went up, but your scan rate also went up. So you should, in theory, get the same C value because they both went up proportionately. Now, of course, if what you're saying is like, well, it's different, it's like you might just have some measurement error if it's different. Like if what are you saying here? The scan rate increases, the current increases. So the reason the scan rate increases, the reason the current increases when the scan rate increases, you can almost just look at it as a direct consequence of the equation that I wrote, which is just a fundamental reality. This is just a sort of definitional kind of a thing. I don't know. Is it a name?
Oh,
what's the equation? I mean, this equation.
What, this equation. So that is that's the derivative of the equation that describes the charge of a capacitor. So the charge on a capacitor is Q is equal to C times the voltage.
Q is equal to C times
just the voltage.
And then you take d dt of the whole thing.
Yeah.
Basically.
Yeah.
D dt. And so dq dt is current.
Yeah.
Change of charge over time, which is like coulombs per second, right? Is equivalent to amps, which is current, and dv dt is scan rate.
Yeah.
Right. So there you go. Thank you. So by virtue of this, why does the current go up when the scan rate goes up? Because direct from this equation here, as they have a direct relationship, right? As the scan rate goes up, so the current goes up. And in fact, what I would suggest again is that any differences in the capacitance, unless it's like a lot different or whatever, the only way that as the scan rate goes up, the current goes up, that wouldn't be true is if the capacitance weren't constant. But considering the capacitance should be roughly constant, ideally, exactly.
Yeah.
Then this is fixed right here, right? So as this one goes up, this one goes up. If this one goes down, this one goes down. So they're just directly proportionate to each other. So, And let me see here. Does that mean that it's more conductive material when the capacitance decreases when the scan rate? Yes. I mean, again, I think it's just that this could be just something that's like, it depends on how fast you start to scan. You might just get distortions. Like, there's other things here. I don't want to open up a massive can of worms, but like, as we know from our experience working at this company, like as you scan really fast, you have like filter settings and things like that might affect, right? Like I'm just, again, I don't want to open up a total can of worms, but you might be running up into instrument things. Like if you scan really fast, the potentiostat can be, it can get into like oscillations and stuff. There's a lot of stuff. And then if it's if the capacitance is decreasing, it might just be, again, it's just like measurement error. Like if it's decreasing slightly, it might be like it's constant, but you're just over some range, it'll be roughly the same. And then as you start to go really, really fast, the accuracy of the measurement, because it's so quick, might just drop a little bit. I don't know, something like that.
Yeah.
Parasitic losses. Yeah, I don't know if there's something going on there.
So we described it, kind of mathematically. Conceptually, one way to think about this is current is, and kind of as Neil described, it's the rate of charge per second. And so as you reach new voltages as you're scanning, the rate of, you're going to keep increasing the charge. So you have a flat current because, the current just kind of remains flat, which means that it's continuing to charge, right? If the current just dropped to 0, then you are no longer charging the capacitor. So that's another thing to think about. Like as you keep moving to new potentials, you are charging and discharging the capacitor at a specific rate as it tries to move from one voltage to the next. And as you go to faster and faster scan rates, you're moving to voltages that are higher and higher in fewer amounts of time. So it is necessary that the current has to increase to meet that amount of charge. Now, what we also described was a capacitor in the most ideal sense. Like that's the theoretical definition of a capacitor. But as Neil mentioned, if you have, there is resistance, like there is a little bit, there's a little bit of resistance, there's a little bit of capacitance just in things like there's cell cable capacitance, there's just resistance in like connectors, things like that. All those things, and as I think even Chris is also mentioning,
he just said this too. Basically,
as
you at higher frequency, and by that we would mean fast scan rate, like really fast scan rate corresponds to like really fast frequency. A capacitor's impedance starts to drop and it begins to almost become a resistor at a certain point. So
let's see.
The total area is higher.
What is he saying here? The total area is higher?
Like on the CV.
The total, yeah. Are you talking about like not the area of the capacitor? Your capacitor isn't going like this.
Yeah, I don't think
all of a sudden.
I assume you mean the
total
CV.
area is. Oh, you're measuring the total amount of charge, just like the current over time, sort of say. The total area is higher as you go to faster scan rates, or
so as you go to faster scan, capacitance is decreasing as the scan rate increases. I mean, it might be something also to throw out a possible explanation that feels lazy, but I think is often the answer a lot of times, is that you might have a degree of what you would call pseudocapacitance. Like it's not behaving perfectly ideally as a capacitor. And so it doesn't perfectly behave all that well. You might have something like that. Like, I don't know. I mean, you're working on a material that is a supercapacitor, possible material for supercapacitor. It might not be perfectly ideal capacitance for one way or another. And so maybe it doesn't follow this trend that we're talking about perfectly, something like that. I don't know.
We need to know a little more because like if you have a solid state system that like very easily reproduces things, but if you have a, some of these supercapacitors are based on like double layer behavior, and sometimes it's funky. Some of the electrolyte interactions and reproducibility of the double layer can be kind of weird. Let's see. Is it total energy stored increases at higher potentials? So you have more total energy stored at a higher. Yes. So the amount of energy, the total charge, is going to be bigger at a higher voltage, depending on what the capacitor is, just based on that
this
equation.
Is good advice. Run impedance on it at 0 volts and max charge voltage.
Okay.
See what the impedance capacitance shows, if there's a difference, because you might have a voltage dependency of some kind, something like that.
Interesting.
Impedance is a good diagnostic here for sure.
Yeah. Yeah, interesting.
Yeah.
Interesting.
Well, follow up, Santiago, please feel free. I know we're trying to kind of talk through, along with Chris's help. Thank you, Chris, to try to see what advice we can give you. Some of what we said might be useful. I'm not sure if all of it applies to your system exactly. But yeah, feel free to comment if you want to keep the discussion going. I want to touch on, I think Nive's got a question here. How to choose the appropriate equivalent circuit model from the Nyquist plot of impedance data. Sometimes 2 or more electrochemical circuits fit perfectly to our ES data. That is the question of the decade, is it not?
Oh yeah.
There is no answer to this question, unfortunately. One of the difficulties with impedance is that there are almost an infinite number of circuits that can fit your data. I mean, there's some finite amount, I suppose, because you can't have more circuit elements than you have data points. You'd be overspecified. But the answer is for you to try and understand the phenomena that are occurring. So for instance, if you can fit 3 Randles elements and it fits really nicely, but there's no situation where you can explain from a chemical phenomena why you have 3 Randles elements. Do you have 3 charge transfer processes, 3 interfaces? Maybe you do. Great. But if you don't, and there's no way to even conceive of how that's physically happening, then you probably shouldn't use that, because it's more likely that the appearance of 3 distinct charge transfer processes is more likely, I don't know, measurement error or some kind of coincidence or something than a true chemical phenomenon. So what you always want to do as a researcher and as a scientist is combine your desire to make your electrochemical model fit your data nicely with your knowledge as a scientist of what is actually happening in your system. It's very critical, because you're not just fitting lines and dots. You're not just fitting resistors and capacitors and CPEs and Warburg elements to make a little thing look all nice for your publication, for your for your conference presentation. Those things are important. I'm not trying to say they're not, but ultimately as scientists, we're trying to explain the phenomena that are occurring. And so make sure you have reasoning behind one model or another, because a lot of times that's the only, there's a fly in here and I want it gone.
Yeah.
Sorry, I lost my train of thought because a fly flew in front of my eyeball. When you have 2 models that fit almost perfectly, as you said, the only definitive way to say one compared to the other is the one I should use is if you can explain what each circuit element corresponds to more accurately for one than the other. That's why you would pick one. A lot of times you'll find in the literature, and I have a webinar I'm doing in a couple of weeks as well, where I will discuss this in more detail. Be doing some impedance webinars over the next several weeks. So there's a shameless plug for you. Keep in touch with our website, pineresearch.com, and you can see me updating that. You want to be able to try to overlay, for instance, the circuit on your electrode surface. The interfaces, basically, how many interfaces are there? How many Faradaic, how many non-Faradaic processes are occurring? Those are the kinds of questions you want to ask yourself, because that may open up the door. Well, one of these fits really well, but it's overspecified, or one of these fits okay, but it's underspecified. Those kinds of things. So you want to try to think that through as best you can. Other than that, there's no mathematical or algorithm or easy answer from some sort of easy mathematical tool that can tell you this is the right one or that's the wrong one, because we have to use our intelligence. This, as much as it would be great to have AI answer everything for us, or have the computer algorithm or the software fitting give you the answer. The reality is that human ingenuity is still required in this field. So you have to use your intuition, your intelligence, and hopefully that can guide you into the direction of which of those models is more appropriate. Assault gun. An assault gun. See what you did there.
Also, Habji, thank you so much for becoming a tier 2 member on our YouTube channel. We really appreciate it. When you guys become members, that helps support Pine and our digital efforts to be able to do these types of live streams and webinars and YouTube channel stuff, and just providing as much content as we can for free, at no charge. So when people join to become members, we really appreciate it. So thank you, Hopji. We appreciate you joining us. Well, I think those are all the questions that we have so far, both on LinkedIn as well as YouTube at the moment. Just looking, and then Twitter, X, of course, is we're not on there anymore just because they changed some of their policies about streaming, but we may go down that route again, possibly in the future. But let's see, are there any things that we want to mention while we wait for a few more?
There is a meeting in Hawaii in a couple weeks.
That's right.
The Electrochemical Society meeting is in Honolulu. So I will be there with my colleague Tim. So if you are in Honolulu in 2 weeks, it's like the October 6, 7, 8, 9, 10 in that range. Come join us. Chris is still on about the flies. I appreciate it. I'm very old school. I just put out a bowl of wine with soap and it collects them and they drown. I did that to try to collect them, but it's getting desperate. They're all over the place here. And I don't know if we just have too many banana peels in the garbage can and it's getting out of hand. Anyway,
I thought you said oh, I know how to take care of this. First, I got a bottle of wine and invite the bugs on a nice date. Just like we're on a romantic dinner.
Oh, I thought you were going to say, first I get a bottle of wine. Then I get so intoxicated that I don't remember what I was upset about. And then I pass out and then I wake up and then I don't remember why I was mad, but I'm happy.
But then you're happy.
Or hungover, but
yeah.
I could have gone either direction.
Yeah, I could go either direction.
Oh, that's a little goofy.
So
good. Join us in ECS in Hawaii if you're going to be there. We'll have a nice time. It is Hawaii after all, so
yes.
I think it'll just be me next week. I think I should be here.
I will be giving a talk at Villanova next week in Philadelphia, so I will not be here next week.
Okay. But join me on Wednesday. There will be a link to sign up soon. It doesn't exist there yet, so I'm plugging something that you can't do because I'm very, very good at this. But I'll be doing a webinar sort of by popular demand. This impedance webinar has been pretty nice and well attended in the past. I hope it's helpful for people. I like to give it once a year or so. So folks can get the information live again, and I'll be doing that again next Wednesday, October 2nd, 2 time slots. Hopefully for folks in different time zones, it's a little accessible.
Yeah. We'll promote this. We'll let you know about it on LinkedIn, on YouTube, and on Twitter, and our social media platforms, our website, stuff like that. So stay tuned on our social media platforms for news from Pine Research, especially. Upcoming free webinars and things like that we have. Do I have any information about the Villanova event? So I'm gonna go to Villanova on October,
was it the 3rd?
4th is the next Friday. I will just be at Villanova. It's actually a career talk for the chemistry department. And I am working with some of the collaborators from an electrochemistry workshop that I held earlier that week. So it's going to be at Villanova. It's probably, I think it's at 3 p.m. is the career talk. It's like a 50-minute type of thing. But yeah, HubG, if you're in that area, because there are a lot of colleges and universities
in Philadelphia,
in that Philadelphia area.
Villanova is in Philly. It's not in Philly, but it's
not in Philly.
I mean, Villanova is near Philadelphia, I think.
Yeah, it's like a 20-30-minute drive.
Yeah, it's close. I know, like Drexel's there, UPenn is there.
Yeah, I'm trying to think. I can't remember if it's like, I think Villanova University is in Villanova or it's in Lancaster, and I never remember which one.
If it's not in Villanova, that's false advertising.
Yeah, I know. It'll be in Mendel Hall if that's if that's helpful at all. That's where.
Just reminds me of Boston College. University of Boston College.
Yeah,
it's not in Boston. It's not a college.
But University of Boston.
No, Boston College. Like Boston College. It's not in Boston, and it's not a college.
Wait, so if I type in Boston College,
that's the name of the school, but it's not in Boston, and it's not a college. It's in Chestnut Hill, and it's a university.
Ah, okay.
So
so Boston. Yeah, that's right. Boston College is a university,
and it's not in Boston.
That's right, and it's not Boston. Yeah.
So we used to call it. I'm from a school that competed with Boston College. So if you're there, I'm not sorry. I don't like you. I don't like Boston College. We were rivals with them when I was an undergrad. And so we used to make fun of them by calling them Chestnut Hill University. Anyway,
yeah.
That just made me think of that because you're talking about Villanova is not in Villanova or something. Anyway, it's kind of funny.
Yeah, there's a lot of
name place. Like yeah. It's in Villanova on Lancaster Avenue.
Oh,
okay.
Yes. Yeah.
So it is in Villanova, but it's Lancaster Ave. I got it. Because there is a Lancaster, Pennsylvania too.
Yes.
Right. Yeah.
Okay.
Got it.
Well, yeah, HubG, you can reach out to us. I'll just have a general, I'll just share the pinewire email. If you want more information, you can email pinewire@pineresearch.com, and then you can, just say attention to Alex and then ask about, the event and stuff like that. It's not like a huge event. It's just, you can, of course, always ask electrochemistry questions, and we can go into more depth about some science stuff. But yeah, there's a chemistry course, and they usually try to have invite speakers for different things, especially to talk about careers, because doing sales in the sciences is a career that you can go into, and that's not what most people know or think about. They just think that they can be bench chemists and or professors. Those are the only two types of jobs, but there's really a bunch of different types of jobs you can have as a chemist, or even an electrochemist, for that matter. So so that's the event. So that's the only reason why I won't be in next week, and I'll just type in that it's on October 4th. Yeah. So just in case. But yeah. But if you're there in person, that'd be great. Nice
cool.
to know.
Happen to talk with someone here who's going to be where you are next week, so they can say hi in person.
Randomly.
Nice.
Yeah. Or if it's not in anybody's way.
Yeah. Fly to Philadelphia for a day. Meet Alex.
Yeah. I mean, I actually am just flying in for the day. Like, I'm flying in the morning. I'm going to meet with, whoever's there and address or entertain any questions, work on the next workshop that we're planning. But then talk about careers in chemistry. So
very cool.
But yeah.
Well, thank you, everybody. We're going to wrap it up here. I think there didn't appear to be any other questions, so we're going to wrap it up. And if you have other questions, please feel free to leave a comment below on the YouTube video. We'll be happy to answer it in the comment section or on the next episode of Ask Us Anything About Electrochemistry. And look out for some of those events that we talked about. And we hope everybody has a great weekend or rest of your day or whatever day or time and universe that you're existing in at the moment. Yeah. Thank you very much. We appreciate it. Take care, everybody.
All right. Bye.